Yep, this one. So starting with this paper, February, March 2023 and paper 5-2. So the first part of the question is that they have a reaction. And in that reaction, you've got, let me open this as well, just a second. So they've got a reaction that's going on. And in that reaction, you've got Fe2 plus and Ag plus 1, they're reacting. So he's adding iron 2 plus. Ions are usually kept in acidic conditions to prevent them from readily oxidizing to Fe3 plus. Fe2 plus and Ag plus 1. The reactant and redox reaction and the following equilibrium is established. So you're reacting Fe2 plus with Ag plus 1. That's what's happening. So this is the reaction that's taking place. And the concentration of Fe2 plus aqueous at equilibrium can be found by titration with a standard solution of potassium manganate 7, KMnO4. So he's saying, so this is what's happening that, let me just, now this is a reaction. And so the reaction is this one. That you've got Fe2 plus and it's reacting with Ag plus 1 and they're forming an equilibrium. It's producing Fe3 plus and silver solid is being produced as well. Now remember, silver is a solid, the other ones are all aqueous. And he then says that the concentration of, he then states that the concentration of Fe2 plus can be found by titration with KMnO4. Acidified KMnO4, that's what's written over here. So once at equilibrium, the rate of forward reaction and the rate of backward reaction would be equal. And he goes and titrates the Fe2 plus that's in the solution with KMnO4, finds the moles of KMnO4, finds the moles of Fe2 plus. That's how he's going to find the moles of iron 2 plus ions in the titration, in the experiment. So the concentration is found, and then he's able to figure out the concentration, the value of Kc using product over reactants, right? So Kc is, silver is a solid, so that's not written in the expression. So Kc is your normal Kc expression. It's Fe3 plus concentration. That's your products divided by your reactants, which is what are your reactants? It's Fe2 plus concentration, aqueous, and silver ion concentration, that's also aqueous. So that's your Kc. Silver, remember, is in the product side is a solid, so that's not written in the expression. As a what he does is that he adds 100 cm³ of 0.2 mole per dm³ silver nitrate and 100 cm³ of 0.2 mole per dm³ silver nitrate initially in a 500 cm³ conical flask and stopped the flask and labeled it conical flask A. So can anyone, so 100 cm³ of 0.2 mole per dm³. So he adds 100 cm³. Can anyone tell me how many moles he's adding? And the
0.02.
Okay, the other one is also 100 cm³ of 0.2 mole per dm³, right? So the moles that he has initially added, that's 0.02 moles of this and 0.02 moles of this as well. So he's added 0.02 moles of both of them. Just give me 1 second. So he's added 0.02 moles of both substances in the equilibrium mixture. Now, it's going to reach equilibrium, so the moles will decrease. The moles of the products, there's no products initially. So the moles of the products will increase, and the moles of the reactants are going to decrease. Okay, there's going to be a bit of a forward reaction. And this is what's going to happen. And he leaves the conical flask A for 4 hours, shaking it intermittently, then leaving the conical flask A untouched for 1 hour. So he waits for the equilibrium to reach. So this is your solution A. This probably entire thing, this entire mixture, that's your solution A. And so that's your solution A. And after that, what he's going to do is using a pipette, he transfers 25 cm³ of the solution from the conical flask A into a clean 250 cm³ conical flask and label this conical flask B. So he transfers this solution, and this is probably for titration. So what he then does is that he takes, remember this was a total 200 cm³ solution, because it was 100 cm³ of one solution mixed with 100 cm³ of another solution. So the resulting mixture that's now been taken out into a conical flask, and only a 25 cm³ sample. So it obviously contains iron ions and all the products and reactions will be present in this thing. Then what he does is that he adds NaCl to it into B, and a white precipitate of silver chloride is formed. So what he does is that NaCl is added to remove the silver ions probably. So the silver ions are removed because silver ions if you add Cl ions from NaCl, they're going to form an AgCl solid precipitate. So what he's doing is that he's removing all the silver ions from the mixture. He's forming a precipitate, a white precipitate. So the silver ions are removed. And using a measuring cylinder, he adds a bit of sulfuric acid to it, and he rinses the burette and fills it with KMNO4. Now he's doing the titration. So now he's basically adding KMNO4 from the top.
सर उसने AgCl क्यों ऐड किया?
नहीं, NaCl ऐड किया था. He added NaCl
to make AgCl.
Need to get rid of Ag+1 ions. उसका white precipitate form when he added NaCl.
Okay.
So the only thing that will form a white precipitate is silver ions. Okay, and now what he's doing is he started titration. He started adding KMNO4. So your solution has Fe2 plus ions, right? The silver ions have been removed, and he probably removed them because the silver ions would probably also react with KMNO4. He did not want that to happen. He just wanted Fe2 plus to react with. So before doing the reaction, he removed the silver ions, even before starting the reaction. I said then the next part is the KMNO4 in the mixture in conical flask B until an endpoint is reached. He empties the conical flask and rinses it with distilled water ready for the next titration. So you're going to repeat the titration to get reliable results. So this is your table. This is the amount of KMNO4 that's being used. That's a typical titration table. So what is the amount that's used in the first experiment? I think that's 10.60, 10.50. What's the amount in the next one? That's what is that? That's what is 20.35?
9.65.
Okay, that's 9.65. So the next one is probably, what is the next one?
9.9.
Okay, that's 9.9. Okay, and the last one is I think
9.75.
9.75. So which titrations are your best results?
The last three.
They have to be
titration 1 and 3.
1 and 3.
Oh.
1 and 3. 1 and 3 are like really one. I just saying that 1 and 3. Sorry, I forgot that there was a rough one as well. So 1 and 3. They have a difference of. They have a difference of 0.1. Concordant results. Difference of 0.1. So those are your best titration results, and if you take the average, that's going to come out to be 9.7. So you're going to show this.
Sir, difference 0.1 से ज़्यादा नहीं होना चाहिए.
हाँ.
Okay.
So take the average 9.65 plus 9.75 divided by 2, and that will give you what? 9.70. So over here, what is the amount of KMNO4 that's being used? That's 9.070 cm cube on average that's being used. And he also gave us the concentration of KMNO4 somewhere. Like what was the concentration of KMNO4? It's not mentioned anywhere. The concentration of, no, it's just KMNO4. They haven't really mentioned KMNO4 concentration anyway. So what is meant by a standard solution in step 6? So probably he's not asking for any calculations after this. So what is meant by the standard solutions in step 6?
Solution with a known concentration.
The standard solution is the one, because remember in titration what happens is you always have an unknown concentration, like over here. The Fe2 plus over here is unknown, right? And you always titrate it with a known concentration. So that's your standard solution. So the solution with the predetermined known concentration. So then the next part is suggest why conical flask A is left for 4 hours. Why did you leave the mixture for 4 hours? I mean, this one, when he made A, he left it for 4 hours. What was the purpose of leaving it for 4 hours?
To reach equilibrium.
Okay, so obviously he wanted the equilibrium to be established. He wanted the rate of forward reaction and backward reaction to be so that the mixture attains equilibrium. And so why conical flask is not shaken during the final hours? So why did he wrote in the steps that he would shake it intermittently, but then he left it untouched for 1 hour. Why did he do that? Why did he stop shaking the mixture? Like in the
he gets the concentration at the equilibrium. Equilibrium is not disturbed.
The equilibrium is not going to be disturbed if you shake it. Equilibrium is disturbed by pressure, by temperature, by changes in concentration. I mean, shaking something that's not going to, I mean, shaking will only speed up the reaction. So the only thing it will do is it will speed up the forward and backward reaction simultaneously and equally. So it will not disturb the equilibrium position. Okay? So shaking will have no effect on that. What it would probably do is that there's a solid being produced. So you probably wanted the solid to settle at the bottom, because if you keep shaking it, the silver solid is not going to settle at the bottom. Okay, that would probably be the reason for this.
But sir, is Fe3 plus not interfering with the titration?
No, KMNO4 is an oxidizing agent, right? Fe3 plus does not get oxidized. I mean, Fe3 plus does not have further oxidation states. Normally it doesn't.
Okay.
Achha, so next part is that the next part. So silver solid probably settles at the bottom. Okay, that's why he stopped shaking it. Suggest why a measuring cylinder is the most appropriate apparatus to use for measuring sulfuric acid. Now remember this: whenever you add KMNO4, it's always acidified, or whenever you add K2Cr2O7, organic chemistry mein padha hua hai, theek hai, it's mostly acidified. So why do you measure the acid using a measuring cylinder? Like sulfuric acid was added, but why did he use a measuring cylinder? Is measuring cylinder accurate or not?
It's not.
Okay, so your measuring cylinder is not accurate, but is it quick?
Yes.
Yes.
Okay, so it's so the first thing is the reason you're using a measuring cylinder is that it's although it's inaccurate, but it's quick. Plus,
सर वैसे what do you mean by quick? उसमें mixing चलती होगी.
burette की nozzle छोटी सी होती है ना, so burette takes a very long time for the liquid to pour out.
Okay.
Same applies to pipette as well. But a measuring cylinder, you can just tilt it and the whole thing falls into the container. But anyways, it's inaccurate but quick. The reason is that sulfuric acid is just used as it's used in excess. So you don't have to measure exact quantities. Okay, whenever you write acidified KMNO4 or acidified K2CR27, the sulfuric acid is just added in excess randomly. You don't add a very specific amount to it. It's just that H+O9s are needed for the reaction, which is why you just add a bunch of H+O9s into the solution. So
write that inaccurate and quick also.
Suggest why a measuring cylinder is the most appropriate apparatus to use. It's inaccurate because you don't need accuracy because you're already adding it in excess. So you don't have to measure an exact amount. State what the burette should be rinsed with in step number 6.
KMNO4.
Okay, because you're using it for KMNO4, so it's better to rinse it with KMNO4. Okay, so if there's any liquid remaining, that is KMNO4 in it. So it will be contaminated by KMNO4, and that is what you're using it for. What is the color change in this titration? You're adding KMNO4 from the top and there's Fe2 plus at the bottom. So what is the color change?
Purple to colorless.
Colorless to purple.
Okay, it's going to be colorless to purple. Okay, remember KMNO4 color change is purple to colorless. But in the titration, if the KMNO4 falls into the flask and it reacts, it will be colorless. Like purple KMNO4 droplets fall from the top, from the burette, into the conical flask. And if it falls into the conical flask, it will change color to colorless. So as long as the reaction is happening, the KMNO4 remains colorless. It will continue to change from purple to colorless. But the moment
सर आयरन के कलर नहीं लिखेंगे?
आयरन 2 प्लस का उसको लाइट ग्रीन पेल ग्रीन कर सकते हो.
मतलब लिख सकते हैं ना?
हाँ, probably लिख सकते हो. लेकिन ये क्लियर है कि स्टार्ट में its KMNO4 is just going to remain colorless, ठीक है? Because it will continue to react, so it will continue to turn colorless, right? But the moment Fe2 plus is gone, it will become, the purple KMNO4 from the top will remain purple because it's got nothing to react with. So one extra drop of KMNO4, and there's nothing to react with, so that purple KMNO4 remains purple. Now, if it remains purple, that means, and it won't be purple, it would be kind of pale pink. Okay, there's only just one extra drop in a very dilute solution, so that purple color would probably be very diluted. So it would appear very pale because there's just one extra drop. So since it's got you can't iron 2 plus, you can't write green, because the problem is that it also has Fe3 plus in it as well, which is kind of yellowish or reddish brown in color. So you can't, so assuming that the concentration is like very low, the solution would probably appear, ye colors hote na, just a second, let me show you the colors. Copy. So iron 2 plus aqueous. Okay, so iron 2 plus aqueous is very pale green. Okay, this is probably a very concentrated solution, but it's very pale green. So I'm starting this is a better example. This is probably iron 3 plus and this is probably iron 2 plus. Now the problem is that the solution has both of them. So assuming that the concentration is like very little, check color marking scheme this one. But usually they just go from colorless to purple. pale pink. But even if you write pale green, not just green, that would still be considered correct. Okay, is this clear?
Yes, sir.
So then he says the student repeats the experiment using a chemophore at a lower concentration. The student obtains a larger mean titer. Suggests one reason why a larger titer is better than a smaller titer.
To decrease percentage
Error
error.
is reduced.
Percentage error is reduced. The error remains the same. But the Burette reading with the error is always the same. It's plus minus 0.05, right? But if the value is bigger, then the percentage error would be reduced.
Okay.
That's the next part. The equilibrium is shown when another student carries out the titration with 0.02 mole per dm cube. The mean titer is 21.1. So now they've got a different reaction and a different experiment, a different student. And he says that the mean titer is 21.1. And now they've actually given you the concentration as well. He says that it's 0.02 mole per dm cube. So that's also provided. So this chemophore is 0.02 mole per dm cube. So he's probably going to ask you for the moles of chemophore. So how many moles of chemophore do we have? What's 21.1 into 0.02 divided by 1000?
4.2 into 10 raised to the power minus 4.
So chemophore is 4 point, is that 2?
4.22 into 10 raised to the power minus 4.
So there's a second. So 4.22 times 10 power minus 4. So what's the moles of Fe? That's going to be 5 times
2 times 1, 2.1 times 10 to the power minus
C significant 2.1. What's after 2.1?
1,
That's 2.11 into 10 to the power minus
3, minus 3.
So we found the moles of Fe, right? In the flask. Now that flask had a volume of 25 cm cube. It was a 25 cm cube flask. So what is concentration? It's moles of Fe2 plus, which is 2.11. Volume, moles over volume, right? So 25 cm cube is how many dm cube? That's 0.025 dm cube. So what is the concentration of Fe2 plus that we're getting?
0.0844.
So we're getting 0.08.
44.
4 के बाद क्या था?
बस सर इतना ही है.
अच्छा सर ठीक है 0.0844 mole per dm cube, right?
So how did that 25 centimeter came?
No, it was already told you that that initially when they had a 200 cm cube solution for the flask, they used 25 cm cube of the solution. So the moles of Fe2 plus are present in a 25 cm cube sample. Is that clear?
Yes, sir.
As for the next part. Suggests why it is not necessary to measure the concentration of silver ions in the equilibrium mixture experimentally. So why is it like he's trying to find Kc, right? Now for Kc, you need the silver ion concentration, but why is he just measuring the Fe2 plus concentration? Why not the silver ion concentration?
Because they have the same ratio.
Yeah, they have the same ratio and they have the same initial moles as well. So which is why, I mean, if you started off with 0.02 moles and 0.02 moles of this, if let's say 0.01 moles react, then according to 1:1, 1.01 moles of silver ions will also react. So they'll still end up with the same number of moles. So because their starting moles are the same and the ratio is the same, so even at the end of the equilibrium, both their moles will be exactly the same. So silver ion moles will be the same as silver ion aqueous concentration will be the same as the Fe2 plus concentration. ठीक है? Is this thing clear?
सर एक दफा पीछे जाएंगे. हमने NaCl ऐड किया था सॉल्यूशन के अंदर.
हाँ तो सिल्वर आयंस तो हमने रिमूव कर दिए थे ना from the solution.
Okay, okay. Mhm.
So we had removed the silver ions initially and we'd thrown it out. Okay, we had filtered. It had formed a press plate and we had gotten rid of it. So we did not care about the silver ions. What we did was we did KMNO4 titration with Fe2 plus. That's it.
Okay.
And we found the concentration of Fe2 plus. So we found the concentration of Fe2 plus.
Sir, can we not find the concentration of Fe2 plus if we find out the concentration of Ag plus ions first using the amount of NaCl that was added?
You can do that. Or you can find the mass of AgCl, find the moles of AgCl, and then you can find the moles of Ag plus 1 ions as well. But he's not doing that.
Okay.
I said determine the decrease in concentration of Fe2 plus from the initial solution, hence determine the concentration of Fe3 plus in the equilibrium mixture. If you are not able to, so now he's asking you to find out the equilibrium concentrations based on what you have figured out. ये क्या आई थी concentration of Fe2 plus over here? It came out to be 0.0844, right?
Yes.
So we had found the moles of Fe2 plus, and we have the concentration. Remember, this is the concentration of the solution at the end once equilibrium has been reached. So now it's an equilibrium question. Now what you have is, let me rewrite this. It's Fe2 plus Ag plus 1, and it's forming Fe3 plus Ag, that's solid, right? So what is your initial concentration of Fe2 plus and Ag plus 1? What did they give us the initial concentration? What is the initial concentration?
0.02.
And why is it 0.02? यहाँ पे क्या लिखा है? The initial concentration was 0.2 mole per dm cube, right?
Yes.
So the initial concentration was 0.02 mole 0.2 mole per dm cube. But ऐसे ये part थोड़ा सा tricky होगा, just a second. Do you know what happens if you mix two solutions together? What happens to the concentrations when you mix two solutions together?
Increases.
It decreases. They both get diluted, right? So
Increases
basically,
or
how many
decreases?
moles did you add? You added what's 0.2 into 100? We did calculate that. So it was 0.02 moles that were added, right? And then concentration times volumes, we figured that one out as well. This was 0.02 moles as well, right? Now, these were the moles that were added into the solution. But once you add 100 cm cube and you mix it with 100 cm cube, now your total volume is actually 200 cm cube. Is that point clear? That you added these many moles, but when you mix them together, the volume has changed. It is no longer 100 cm cube. These moles are now in 200 cm cube. 200 cm cube is how much? It's 0.2 dm cube, right? So these moles are also present in 0.2 dm cube. But the idea clear, okay? So the concentration, the new concentration, once the two solutions have mixed, is actually 0.1 mole per dm cube. And this one would be exactly the.
Sir, can you explain this again?
The initial concentration was 0.2 mole per dm cube when they were not mixed, right? He took 100 cm cube, 0.2 mole per dm cube. He took another 100 cm cube, 0.2 mole per dm cube. So how many moles did we add? We added 0.02 moles, right?
Yes, sir.
Or इसके कितने डाले थे? इसके 0.02 moles were added, right? So 0.02 moles were added of both of them. And now the problem is that if you add 0.02 moles and if you mix them together, so the volume has changed. It's no longer a 100 cm cube solution. 100 cm cube has mixed with 100 cm cube, so your new volume is actually 200 cm cube. So these moles are actually in 200 cm cube. Is this idea clear?
Yes, sir.
तो फिर concentration क्या होगी? That's going to be you have these many moles, but in 0.2 dm cube. So that becomes 0.1 mole per dm cube. Iske bhi, you had these many moles, but the solution now is actually its volume has changed. It's 0.2 dm cube. So its concentration will be 0.1 mole per dm cube, right? So remember this: whenever you mix two solutions together, both of their concentrations will decrease. So your new starting concentrations are actually 0.1 mole per dm cube once you've mixed them together. So the initial concentration of both Fe2 plus in terms of concentration, that's 0.1 mole per dm cube. And this one is also 0.1 mole per dm cube. ठीक है? Is this?
डिक्रीज क्यों हो रही है? वॉल्यूम का इंक्रीज करने की वजह से।
हाँ, concentration क्या होती है? Concentration moles over volume होता है ना? तो moles तो वही रहे ना? पहले तो मसला था कि वो जो moles थे वो 100 cm क्यूब में थे ना? और इसके मोल्स जो थे वो कितने में थे? वो भी 100 cm क्यूब में थे, लेकिन जब दोनों को मिक्स कर दिया तो अब तो वॉल्यूम चेंज हो गया, अब तो 200 cm क्यूब हो गया। यानी मोल्स तो वही रहे हैं, लेकिन वॉल्यूम जो है वो 200 cm क्यूब हो गया। तो दैट मींस कि इट्स बिकम डाइल्यूटेड बिकॉज नाउ देयर इज एक्स्ट्रा वॉल्यूम, राइट? ठीक है, इज दैट क्लियर?
यस सर।
Sir, you don't do that for every KC expression, do you?
In other KC expressions, you're actually dealing with moles. We could have done two things over here. What we could have done was that we could have straight away solved it using moles. That is one thing that we could have done. So another thing that we could have done is we could have instead of actually dealing in concentrations, okay, same expression. So what we could have done was that we had how many moles? We had 0.02 moles, right? So instead of concentration, we could have solved it using moles. So our initial moles were 0.02 and these were 0 and these were 0. And then we had to find the moles at equilibrium. So the concentration had decreased to, it had decreased to 0.0844 mole per dm cube, right? So how many moles would solution A have? I mean, the concentration has now decreased to 0.0844. So concentration multiplied by the volume of solution A, which is 200. So how many moles do we get? What's 0.0844 into 200?
16.88.
You divide by 1000 as well.
0.01688.
So 0.01688.
0.01688.
And the moles of Ag plus 1 will also be exactly the same. So that means how much reacted? Like you started off with 0.02, 0.02, but now you have 0.01688. So how much reacted? Like what's the difference?
3.12 into 10 to the power minus 3.
3.1?
1, 2.
Ten per minus 3, and this would be 3.12 times 10 per minus 3. This is the amount that is reacting, right?
Yes.
So on the other side, this is the amount that's going to be produced. So 3.12 times 10 to the power minus 3 moles got produced, right? And silver solid would be exactly the same. And remember, it's a 200 cm cube solution, so you can now convert it into concentration, which is going to be what? Divided by 0.2 dm cube. This will be divided by 0.2 dm cube. This will be divided by 0.2 dm cube. The last one is a solid, so the term concentration does not apply to it. So what you could have done is you could have dealt in moles. ठीक है, that, and you could have found concentration right at the end. But remember, when finding concentration, because 100 cm cube was mixed with 100 cm cube, your volume was actually 200 cm cube. And now you have to use these values to figure out what Kc is. What do we get for Kc? So it's 3.12 times 10 power minus 3 divided by 0.2. And at the bottom, it's going to be 0.01688. And that's being squared as well.
Is it 0.034?
So Kc is 0.034. Okay, that's our value for Kc, and let me just check what this value is. That's a 0.03. That's at the end. No, we are getting.
I am also getting 2.19.
2.19, right?
Yes, sir.
So that's a Kc, right? 2.19. If you're getting 2.19, then we've done it correctly. Where's the working?
Okay, it was 2.19.
2.19. So anyways, but did you understand the fact that what needs to be done is you would have to find the moles of the starting moles. So the starting moles were 0.02 moles and 0.02 moles. You had to find the final moles. Over here, we calculated concentration, right? Which was 0.0844 mole per dm cube. This was the same concentration of Fe2 plus. I mean, because it was the same solution, so it was the same concentration. So we found out the moles. This was in 25 cm cube. What we could have done was we could have used the moles that we had calculated earlier and just taken ratios and found out the moles in 200 cm cube. Or we could have done the used concentration and multiplied by the volume, and we would have found moles that way as well. Okay? So we're getting the right answer in this case. So that's a typical Kc question. Achha, is this clear, this one?
Yes.
Yes, sir.
Okay. So I don't think there was apart from this fact 2 points. Okay? There were two main points. One was that, remember, when you dissolve two solutions together, their concentration decreases. We didn't use that actually. हमने तो skip कर दिया था. Previously we started off. I mean, I wanted to solve the question in Kc in terms of concentration, but then we skipped 2 moles, right? And then we found it, and then we converted the final moles to concentration, and then we found Kc. But remember, this is fact that whenever you mix two solutions together, both their concentrations are going to decrease mutually. Okay? So, okay, we'll do the next question next time. Okay?
Okay, sir.
सर एएस की क्लास होगी?
हाँ, वो है 10 minutes में. ठीक है.
ओके.
Okay.
एंड सर सुबह हुई थी?
नहीं, सुबह नहीं हुई थी.
ओके. थैंक यू. अल्लाह हाफिज.
Okay.
Allah Hafiz, sir.
Hafiz.